So in the previous section, we looked at computing our definite integrals geometrically by sketching out the graph and trying to figure out what the area is. And we looked at evaluating definite integrals by using different properties. Both of those are very tedious. So what our goal is in section 5.3 is to be able to evaluate definite integrals in a more efficient way. We're going to start out with defining an area function. So if we look at example 1, we're going to define this area function a of x to be the integral where we're starting at -4 and we're going to whatever x value we put in of this function f of t dt. We're going to evaluate our area function for x values that are greater than or equal to -4. So first of all, what I'd like to do is sketch the graph for you. The graph is going to be the graph of the horizontal line 2, and we're going to go from -4 to -2. We're going to graph 2. And then from -2 to +2, we're going to graph the diagonal line, y equal to -x. At 2, we're going to graph a horizontal line, y equal to -2. So this is my function f of t. So we put in a t value, we get back a y value or an f of t value. So if I wanted to evaluate this area function when x is equal to -4, the area function at -4 says we're going to substitute in -4 into the integral. So it's going to go from -4 to an x value of -4 of my function. And going back to the properties of integrals, remember that if you have your limits of integration the same, so we have -4 and -4, your integral is just equal to 0. Oops. 0. All right. So let's look at the area function of -2. So that would be the integral from -4 to -2 of our function. Let's look at what this is on the graph. We're going from -4 to -2, and we're computing this area. So it's above the x-axis, and it's going to be a +4. When we compute the area function for x equal to 0, it's the integral from -4 to 0 of our function. So now we're going to 0. We're adding the area of this triangle, and it looks like that's going to be equal to 6. All right, area function at 2 will be the integral from -4 to 2 of our function. Now, once we're going to 2, can you see that this region, I'll call it 1, and this region 2, they're the same, so they cancel each other out, because remember, we're computing net area. Okay? That means this integral is just equal to 4. And then when I evaluate this area function for 4, I'm looking at the integral from -4 to +4 of this function. And I can see that that's just going to be 0. As we go to 4, we add in this area, which is going to be a -4. So this would be a +4, a +2, a -2, and a -4. Adding all those up, we get 0. Now since we have this function, a of x, what I can do is I can just graph the area function. I'll make a table of values, and those are the values that I got above, where I put in an x value and I get back an a of x, which is just my y value. So we first put in -4 for x, and we had the area function was 0. Then we put in -2 for x, and we had 4. At 0, we had 6. 2, the area function was 4, and at 4, the area function was 0. So let's go ahead and just plot these points on the graph. 1, 2, 3. This is -4 was 0. -2 was 1, 2, 3, 4. At 0, we had 6. At 2, we had 4, and at 4, we had 0. So if I was going to graph this area function, it kind of looks like a parabola. Okay, so we define this area function, which turns out just to be our integral, and it's net area. Let's look at an application of this area function. And then above in this box, what we do is we have the definition of our area function, which is defined as a of x is going to be the integral. Remember, we're starting at some number, and then we're putting in x values of our function. Notice that the function has an f of t dt, and that's just because we can't use the variable x in our integrand, because it's already being used as the limit of integration. And then this would be the area function on some intervals starting with a, and then we put in whatever x value we wish. Example 2, we have this area function, a of x. We're going to be evaluating this function from 0 to some x value. And the function is 1/2 t plus 1. Part A, I need to find two things, a of 4 and a of 5. When I look at a of 4, it's going to be the integral from 0 to 4 of 1/2 t plus 1 dt. So I'm starting here, let's look at the graph. I'm starting at 0, and I'm going to 4. Well, this is all above the x-axis when you look at this area here that we'll be computing. And when we look at this area, we could see that this is the area of a trapezoid. So let's recall what the area of a trapezoid is. The area of a trapezoid is going to be equal to 1/2 times the height, and then you add the smaller base plus the larger base. Looking at this drawing, if you turn this image onto its side, the height is actually 4. This piece here is the smaller base of 1, and then we have the larger base of 3. So a of 4 is going to be equal to the area of this trapezoid, which would be 1/2 times the height of 4, and then the smaller base is 1 plus the larger base of 3. And that just gives us 8. let's look at finding the area function of 5. So a of 5 is the integral from 0 to 5 of 1/2 t plus 1 dt. If we go to 5, the only thing that's going to change is my h and my big B. Okay? So that's going to be equal to 1/2. The height is now 5. And then the smaller base is still 1. Plus, I think I'm going to use decimals. This is 3.5 for the larger base. In a calculator, that would be 11.25. Okay, let's look at part B. Part B says to find a of x and graph. Well, I know what a of x is. It's that integral. However, let's just look at some random x value here. For any x value, this area function is simply going to be the area of a trapezoid, right? For any x value. So in general, the height is going to be the x value we put in. The smaller base is always going to be 1. That's not changing. But the larger base is going to be this value here, which is your f of x. And in our case, f of x is just going to be replacing x with t on that integrand to get 1/2 x plus 1. So in general, when we're finding our area function is going to be equal to the area of the trapezoid, 1/2 times the height of x, 1 plus 1/2 x plus 1, which simplifies to 1/4 x squared plus x. Notice that this is a parabola opening up. Okay, so if I were to graph a of x, it's just a parabola that opens up. Right, so this is my a of x. I put in an x and I get back some a of x, which is 1/4 x squared plus x. Now, the last part, C. C says to find a prime, or the derivative of a. The derivative is, the derivative of 1/4 x squared plus x is going to be 2/4, which would give us a 1/2 x plus 1. Something you should notice is that this is the same as f of x. And that's actually kind of important. If you go back to when we first talked about antiderivatives, remember that the derivative of a function is called its antiderivative. If we look at this next box here, which is almost to where we want to be. This is the fundamental theorem, but it's only part 1. So usually we just say FTC for fundamental theorem of calculus. So our fundamental theorem of calculus says that if you have some area function, and notice that this is an equation, then if you take the derivative of your area function, it should be equal to your integrand, which means it's the antiderivative. And that works because this is an equation. I'm allowed to take the derivative on both sides. What's going to happen is when we take the derivative on both sides of this equation, we just get that the derivative of our area function is equal to our integrand of f of x, which is the definition of an antiderivative. We're going to use the fundamental theorem of calculus. This is part 1, and at the end of this section we'll be talking about part 2. To simplify some expressions, something to notice is that in the fundamental theorem of calculus, we're starting our lower limit of integration with some number a, and the upper limit of integration is x. So, if I was going to simplify this derivative of an integral in part A, the fundamental theorem of calculus says that if I start with a number, and I'm starting with 0, and I go to just x, that I'm allowed to replace, this will all cancel, the derivative of an antiderivative cancels, and then all I have to do is replace my variable t with this variable x to get x to the 4th minus 3. That's what this theorem is saying. The derivative and the integral will cancel, and all you have to do is substitute in x for t. That's what that expression will simplify to. Let's try this again in part B. Well, the problem with part B is I'm not starting with a number, I'm starting with x. I'm ending with the number 3. However, all I have to do is take the negative of the derivative of this integral, and remember that changes the order of my limits of integration. So now I can start with 3 and end with x, and then use the fundamental theorem of calculus to simplify the square root of t squared minus t plus 5 dt. So by the fundamental theorem of calculus, this is going to be equal to a negative. All I have to do is replace t with x. It doesn't matter what value you start with, because we're not evaluating this expression, we're just simplifying it. So this becomes the square root of, remember what I'm doing, I'm replacing my t with x. So x squared minus x plus 5. So to use this theorem, you have to make sure you're starting with a number on your lower limit of integration and you're ending with x. If not, just use properties to make it look like it should. Part C is a little bit tricky. We don't have x. We're starting with 0, that's good. But this is an x squared. So what I'm going to do is I'm going to do a temporary substitution and do sort of something that looks like the chain rule. I'm going to let, and since I'm not using the variable u, I'll let u stand for my x squared. So the derivative of u with respect to x is going to be 2x. Now here's the fun part. If I take the derivative with respect to x, I can break that up into the derivative with respect to u times the derivative of u with respect to x. Notice that in this right-hand side, the du's can cancel, and I'm back to d over dx. What I'm going to do is I'm going to rewrite this integral, and I'm going to replace d over dx with d over du times du over dx. But since it's multiplication, I'm going to choose, because multiplication order doesn't matter, I'm going to choose to take the derivative with respect to u. Now remember, what I'm doing is I'm just replacing the d over dx. So I'm going to take the derivative with respect to u of my integral from 0 to u of t to the 4 dt, and I'm going to choose to put the du over dx at the end, which I can do since it was multiplication. So now if we look at this first piece here, that fits the fundamental theorem of calculus, which says that the first part will cancel and all I have to do is replace t with u. So this is going to be u to the 4th times du dx is just 2x. However, we were supposed to simplify with respect to the variable x, not u. So I'm going to substitute back the x squared for u, and this becomes x to the 8 times 2x, which is simply 2 times x to the 9. Okay, so you see what we're doing here? We're getting it to look like the fundamental theorem of calculus. Again, I have a problem here. This is not x. The upper limit of integration is cosine of x. So I'm going to let u equal cosine of x. And then my du dx is going to be equal to negative sine of x. Now I'm going to replace this d over dx with d over du integral 0 to u t to the 4 dt, and then this would be the du over dx. So again, this first piece becomes u to the 4. So this is going to be u to the 4 times du dx would be the negative sine of x, but I don't want u, I want x. So I'm going to replace the u to the 4 with cosine to the 4th of x times negative sine of x. And that's going to irritate me, so I'm going to put the negative sign in the front times the cosine of 4, or cosine to the 4th power of x. Okay, well, the last example we're going to do using the first part of the fundamental theorem of calculus is E. So in part E, we've got two problems. We're not starting with a number, we're starting with x. And we're not ending with an x, we're ending with an x squared. So what I'm going to first do is I'm going to break these up into two integrals, and I'm going to put in some number, since there's no number in my limits of integration. And I can choose whatever number I want by a previous property we had in our last section. So I'm just going to choose 0. I'm going to break this integral up, okay? And it still has the derivative on the outside. So I'm going to break this whole thing up as the integral, and I'm going to start with the lower x, and I'm going to go to 0 of t to the 4 dt, plus start with 0 and end with x squared. So again, that was a property we had in the previous section that said we can break integrals up with whatever number we want. And now that I have it broken up, I want to look at this first piece. Notice that it goes from x to 0. I want it to go from 0 to x. So I'm going to go ahead and change that to a negative and flip. The other one's okay. The 0 to x squared, we had actually figured this out in part C, I believe. So when we take the derivative of this whole piece, this first one is going to be a negative x to the fourth. And then we have a plus. This second piece here, we found that previously to be 2x to the 9. So this simplifies into 2x. I don't like the negative first. 2x to the 9 minus x to the 4th. That looks nicer to me. And now we're building up to our goal. So this is the goal for this section. This is what's going to make life really easy when we're evaluating these definite integrals. This is the fundamental theorem of calculus, part 2. We usually just call it the fundamental theorem of calculus. Sorry. And it goes back to the idea of the area function being an antiderivative. If you have definite limits of integration, then to evaluate the integral, all you do is you take your antiderivative of b minus the antiderivative of a. Another way to write this is the antiderivative evaluated, and we're going to use this bar, b to a. So it's going to be the top is the b, the bottom is the a, so it's f of b minus f of a. Let's look at how we apply this in example 4a. The antiderivative of x to the third minus x to the negative 2 is going to be x to the 4 over 4 minus x to the negative 1 over negative 1. So we're going to evaluate this antiderivative from 5 to 1. Now I can clean this up a bit. X to the 4, I'll leave the 4 down here, plus, I'm going to write this as 1 over x because it will be easier for me to evaluate. So this is what we do. It's going to be the upper minus the lower. So this becomes 5 to the 4th over 4 plus 1 over 5. So that would be the upper, where you just substitute in 5 for x, minus, now we put in 1 for x. 1/4 plus 1. And after doing all the math, after letting my calculator do all the math, I think it's 155.2. You just have to be careful if you're using your calculator that you don't want to put any repeating decimals in here. If it's a repeating decimal, you should probably switch it to fraction form. Let's try another one. Cosine of 2x, the first thing I want to do is find the antiderivative. So remember, it's going to be 1/2 sine of 2x, and now we're going to evaluate this pi minus 0. Notice that we're not using a constant c, and the reason why we don't have to is because of our limits of integration. These are definite limits of integration. We have definite numbers, which means we're automatically solving for the constant c. So pi goes first, so we're looking at the sine of 2 pi. So it's upper minus 1/2 sine of 0. Well, sine of 2 pi is still 0, minus sine of 0 is 0. So this is simply 0. But this is so nice, right? Because now we don't have to create areas and kind of look at it geometrically, or we don't have to use property. we can just use our fundamental theorem of calculus. We still have to be a little bit careful. Notice that if I was going to find the integral of my function g from -1 to 7, the problem I have is this is a piecewise function. So is it even integrable? Well, I don't know. So let's go ahead and graph this. Well, we're only going from -1 to 7. Maybe I'll use a darker color. 1, 2, 3, 4, 5, 6, 7. So it from -1 to 1, 2, 3, the graph is going to be the horizontal line 3, 1, 2, 3. So it's solid. And then at 3 is open. And then greater than or equal to 3, it's the graph of x minus 2. So that would be 1, and it goes straight up. And solid, solid. Okay, well, this is integrable. It's bounded. And it has a finite number of discontinuities. So I can either figure out the integral using geometry, but I think I'd rather use the fundamental theorem of calculus. Now I need to break this up into two integrals. I'm going to look at my first integral, right, from -1 to 3. So again, wherever you have a discontinuity or a change in the function, you've got to split it up into different integrals. From -1 to 3, I'm looking at the integrand of 3 dx. And I'm going to add it to the integral from 3 to 7 of x minus 2. So instead of doing it geometrically, I just broke this up into two integrals. The antiderivative of 3 is 3x. And I'm going to go from -1 to 3 plus antiderivative of x minus 2 is x squared over 2 minus 2x. Oops, sorry, that's an x. From 3 to 7. Now sometimes when you're dealing with more than one integral, it gets a little bit messy with that weird bar. So I kind of like to change it into brackets, but you don't have to. It's just clearer for me to see the different integrals. So in the first one, 3x, this would be 9, right? Upper minus -1 means 9 minus a -3. So that would be this first piece. Plus, in this second piece, I put in 7. So that's going to be 49 over 2 minus 14. Subtract the lower, put in 3. You have 9 over 2 minus 6. And then in our calculator, that just gives us 24. The very last example in this section is something that we have to be careful. Notice in this integral in part D, I'm supposed to evaluate this from 0 to pi. So let's just say that 1, 2, 3, this is pi over 2. 1, 2, 3, and this is pi. The problem I'm having is that pi over 2, both secant and tangent are undefined. So if I look at secant tangent and I graph this in my calculator, what we should see is an asymptote here at pi over 2. At 0, we're at 0, and then these two go up. From 0 to pi over 2, secant and tangent are both positive. from pi over 2 to pi, these are both negative, so it's still going to go up. And again, you could just plug this in your calculator. Just graph parentheses 1 over cosine of x times tangent of x. All right, so I have a problem because this is unbounded at pi over 2. Remember, for a function to be integrable, it's okay if it's not continuous, and I can see it's not continuous at pi over 2. But it has to be bounded, meaning our y values have to reach a number. They can't go to negative or positive infinity. So at this time, now this is something that we would reserve for calculus 2. For this, right now, you cannot integrate. On the interval from 0 to pi. Now, if I decided that I was going to integrate this from 0 to pi over 4, that would be okay, but not from 0 to pi. And that's it for this section.